Hello, you should hear me, and I think you can see the desktop now. Does everything seem okay?
Yes.
Yep.
Yeah, okay, great, thanks. All right, so, okay, so here's what we're gonna do today. Look real quick at some new I put a couple collections of problems up on here. So we're gonna look at those real quick, and then we're gonna also look at examples of using recursion. Okay, the homework assignment that you have now that's due on Tuesday, several of these problems are solved using recursion. And the book doesn't really talk much about recursion. It kind of supposes that you've seen it before. So the book doesn't spend a lot of time, or actually any time, talking about recursion. But I thought we should do some examples of using recursion and just do some examples to give you a sense of how you go about doing these kinds of problems. Okay, so we're going to look at some problems that are similar to these problems here that are solved using recursion. Okay, now so we're going to do that, and also in the reading we're talking about polymorphism, and and for the recursion problems we don't need the polymorphism stuff. But let me just show you real quick. We were in class the other day. We were working on these problems here. Oh, I'm sorry. We were working on these problems here. We finished these. We started these. So these were the problems that look like this. Okay. So this was the problems where you're supposed to annotate each of these functions. Okay. Now, I'm not going to finish those. Instead, I've got another set of problems very similar to those that are a little bit harder. Okay. See, these are type declaration problems. Let's see. Oh no, I don't have those up there yet. No, there's these more problems with we finished these problems using patterns. Here's more problems involving patterns. Okay, here's more functions to write using patterns. The function is written without patterns, and I want to translate it to something that is written with patterns. So let's do a couple of these, and we'll see in a minute what's different about them. So this is the new set of problems. And let me download the old set of problems, the ones we finished. I'll show you. So we're gonna, okay. Let me open them in a text editor. Okay, we did these. Okay, see, each one's written as just f of x, f of x, f of x, f of x, and then they're written using functions on the right where you take apart the x. Okay, here's more examples of that. F of x, no, here, g of x, g of x, g of x, g of x, g of x. Okay. Okay, now remember, we saw these. What you want to do, for example, on this one is to write it using a pattern. You'd say function f1 of x. I'll call it f2. Oh, I'm sorry, f1 of, now you want to add one to the head. So think of it as x corresponds to something else. And then, you say, okay, 1 plus x. Okay, that's using a pattern instead of just using this thing. Instead of having to break this guy up on the right, you break him up in a pattern on the left. Okay, and then here was another one, function f2 of x equals. Now, here we want the first thing in the x. So instead of writing x, let's break it up. Let's break it up as x in front of. Okay, now here, remember, this took the head of the tail. Okay, well, the head of the tail is the second thing in x, so we need the second thing in x. Okay, and then that's in front of, well, we don't care what it's in front of, so we can put a blank there. Okay, and then what we're doing is x plus y. Okay, that's written using a pattern. Now, notice it ends up being shorter and it ends up being much easier to read. Okay, you want a list with 2 items, and you're going to add the first 2 items. Okay. Okay. Now, if we put these into ML, these things are what are called monomorphic functions. And that's what we want to switch away from. Here's what I mean by that. So there's the function. Okay. It takes in an int list and gives me back an int. So it adds up lists of int. So it doesn't work with anything but integer lists. Because it's got this sum here, it only works with integer lists. Same with this one here. Because it's got that addition in it, it only works on one kind of list. It only works on integer lists, and it gives me back an integer. So this is not what we would call a polymorphic function. It's a monomorphic function. The idea is that polymorphic functions work with lots of different lists, different kinds of lists. Okay, so let's switch to this other set of problems. These are all polymorphic. Now, they're not really harder, but there's something a little bit different. So let's look at this one. This one's saying a function that takes in a x. Well, what is x? Well, you look here and say, oh, head of x, that means that x is a list. And here's the head of the tail of x. Oh, that means that's the second thing in the list. So what's this function do? It builds a pair. The first thing in the pair is the first thing in the list. And the second thing in the pair is the second thing from the list, because it's the head of the tail of the list. So here's how I can write that using a pattern. Function G1. Okay, X is a list, and I need the head of the list. Okay, and I need the second thing in the list. And I don't care what else is in the list. And my output is X with Y. Okay. Right. Now, that's a lot like what we did a minute ago. It's a lot like this. Notice it's the same pattern here. So you notice that the pattern there was I need a first item in the list and a second item in the list. I don't care. And then I'm going to add the first to the second. But on this one, I need the first item in the list, the second item in the list. I don't care about the rest of the list. And then I form a pair of them. Now, when I put this function into ML, it's got a very different feel to it. The function has these type parameters in it, because this function didn't really care what kind of list that is. This function didn't say it, but it really only works with integer lists, because you're going to do something with the you're going to take things in the list and add them up. And if you add them up, you can only add integers or reals, and by default, you add integers. So since I didn't say otherwise, it's going to add integers. Okay. But in this example, even though I want the first 2 items in the list, all I do is bundle them up into a type. I don't do anything with them as a kind of value. I just say, give me a list, and I'm going to take the first 2 items in the list and put them in a pair. So ML says, well, yeah, you can do that with any kind of list. You can do that with an integer list. Okay. You can do that with a string list. Okay. We don't use integer lists very often because as examples, because they take too long to type. But notice it took the first 2 items in the list. Now I've got a what in Java we would call a generic function. In ML, we call it a polymorphic function. The function does something in a way that says, well, it isn't integer list anymore. It's any kind of list. You give it any list, and it's going to take the first item in the list and put it in the first part of the pair, and take the second item of the list and put it in the second part of the pair. Since you don't say anything about since you make no assumption or put any restrictions on what's in the list, ML's smart enough to say, okay, that's a polymorphic function. It takes in a list of okay, it uses these are called type variables. You read this as a list of type A, and you get out a pair of type A's. Okay, or people just say A list gives me out a pair of A's. We don't really have a good way to read these. These guys are, if you, in the data structures class in Java, you may have seen, well, actually, let me, where you see this in Java, if I like look at Java 11, the list data type, okay? If I look at the list data type, well, a list of what? Well, it could be a list of anything. This is Java's, here is the Java way of writing that. Okay? See, in Java, you say list angle bracket E close bracket. The E is the type variable. So you can create a list of strings or a list of integers or a list of lists. You know, E can be any type, but you create a list of a certain type. In ML, you write it, okay, the type variables in Java, type variable is usually a single capital letter, though there is no rule about what a type variable has to be in Java. I could say a list of Bob, and then Bob is actually a type variable. It just represents the type that I will end up putting in the list. Okay. Then in Java, when you use this, it would look like, if I want a list of color, I do that. List of color. So this is my type, list of color. I'm creating a variable called color list, which is a list of color. And then I would say something like new array list. I can't actually instantiate. There is no list in Java. List is we'll talk about this later on. List is an interface. There are no objects of type list. So you have to create an implementation of it. So I'll create an array list of color. Now create an empty one. Okay, so that would create an empty list, an empty color list. Okay, so the variable has type list of colors, but the object has type array list of colors. And I could also use a linked list of colors. I can't say that in Java. There is no such thing as a list of color object. There are no list objects. This is one of the places where Java is a little bit messier than in ML. Okay. Now in ML, if I want a list of color, I would say color list. Oops. If color is a type, okay, I would say color list. Okay, so that's the type list of colors. Okay, now in the documentation, though, it's written list of E, because in the they're documenting the fact that it can be a list of anything. So you could have a list in Java. I could have a list of string list. That's the type is list of string. The name of the thing is string list, and then I would create a new linked, well, I'll do an array list this time, array list of string, and I'll create an empty one. Whoops. Okay, so that's what Java will look like. Okay, let's see. Yeah. So, and in ML, the generic way of describing things is that color lit. You put, notice Java puts the generic variable after the name of the type, and it puts it in angle brackets. Okay, ML just puts the name of the type in front. But when you want to describe it generically, the type variables have to be lowercase letters with a quote in front of them. So that's the generic type. A list of A. Okay, so this is the parallel to this. and this would be a specific color list. So if I ordered it right, this is the generic type, and there's two examples. In ML, there's the generic type, the polymorph. In Java, this is referred to as a generic type. In ML, this is referred to as a polymorphic type. The words more or less mean the same thing. What Java refers to as generics is what ML refers to as polymorphism. And what's an interesting little fact is Java did not have this for many, many, many years. It took like 20 years before Java got generic lists. And the man who put generic lists into Java was one of the people who created generic polymorphic things in Haskell. Now, he didn't do it in ML. He actually did it in Haskell, which is the successor to ML. But the man who put generics in Haskell, and I think he had something to do with the generics in ML too, he's actually the man who put it in Java, a guy named Philip Wadler. He's a real brilliant person. So he kind of like said, "Oh, I'll help you people out." And he's this really brilliant computer scientist who knows functional programming and abstract programming really well. And at some point, the Java people more or less said to him, "Can you help us? Can you help us get generic lists?" Because it used to be in Java, you couldn't do this kind of thing. You couldn't say list of string and list of color. It was much messier. In the old days, what you had to do was this list of, well, you created a list essentially of, you didn't use this notation, but you essentially created a list of objects. But an object is a reference that can point to anything. In your list of objects, you could fill it with color objects. Okay, so then you'd have a list of colors. And in your list of objects, you could fill it with strings. So then you have a list of strings. The trouble with this was there's nothing from you stopping you from putting 27 colors in there and 57 strings in that list because it's a list of objects. And then programs would get all messed up because there wasn't any type safety. If in Java now, if I say list of string, you can't put a color object in there. And if I say list of color, you can't put a string in there. If I say list of object, now we didn't use that notation. It was just actually called a list. But you actually designed the list to hold objects. And the trouble is you could put anything in the list. And if you thought it was a list of objects, there might be a bug in your program. And if you thought it was a list of strings, there might be a bug in the program and somebody forgot to stringify an integer and put the integer in the list. So instead of there being the string 123, there was the number 123 in the list. And then when you got to that item in the list and you tried to use it as a string, like compute its length, it would blow up on you. And you'd get really complicated, hard to find runtime errors because you thought that the list was a list of strings, but somebody goofed up and put an integer in the list. That can't happen here, and it can't happen here, and it can't happen in ML. But that's what we're trying to get at is modern programming that gets away from this kind of untyped programming, a list of objects, and gives you typed lists that are generic. Now, the thing is, you don't want to have to write there was another thing you could have done in the old days. In the old days, you could have written list of string data type, and you wrote it yourself. Then you wrote list of color data type, and you wrote it yourself. Now, this data type would only hold strings, so you couldn't goof it up. But you had to rewrite it to get list of, you had to rewrite it all to get list of colors. You had to duplicate all the code in here over here, but using colors. And then when somebody said, I want a list of integers, you had to write a list of integer data type. And you basically had to duplicate all the code in here and the code in here, again, for a list of integer. Okay, now that would be type safe. Nobody could put a string in that list, but you had to write the code all over again. Then you had to write the code all over again. This is written one time. You write the generic list of E, and then you can instantiate it as list of string, list of color. Okay, In the old days, you either wrote list of object, which was not type safe, but you could write it once, or you wrote a type safe list of string, a type safe list of color, a type safe list of integer. But then you got really tired of this because when somebody said, oh, now I want a list of doubles, you had to write it all again. And if here, let me show you what that looked like. It's still there in Java. Binary search array of int, binary search array of long, binary search array of short, binary search array of object, binary search array of float, binary search array of double. Yeah, you had to write these things over and over again. We don't need this anymore, but we're stuck. But see, that was put in Java way back in the beginning. Then you go down here and there's compare. Compare two arrays of bytes, compare two arrays of char, compare two arrays of double, compare two arrays of float, compare two arrays of int, compare two arrays of long, long, short. Then you could compare two arrays of object. Now here's the generic one. See, now here's where it starts to become the more modern generic one. These were put in the language much more recently. This was put in the language since Java 9, see? Took a long time for that to end up in Java. See, it took Java a long time to get these generic versions of things. So for a long time, it had these non-generic versions. And the language is full of this stuff. See, copy, 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 copy. Then, there's going to be down here, there's the sort functions. Sort, 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 sort. See, there's sort object, an array of object. For a while, that was the best generic sort we had, and then now we have this one. See, T. See, there's the generic type. Okay, there's the modern one. If Java was designed from scratch, there wouldn't be any of these. There'd be just this one down here. This one was put in there in, oh, where is it? It should say when it was put in there. Usually there's a little clause down here that tells you when that function was added to the language, but it's not in there. Maybe they forgot to write it. They usually tell you when they added a function to the language. It usually says at the bottom, there'll be a thing that says since, it says since, and it tells you when it was, like here, since 1.8. See, this has been there since 1.8. I don't know why this one doesn't have a since. It wasn't there at the beginning, because there was no generic types in the beginning of the Java world. These things were entered into Java in Java 5. So Java 5 got generics. So this function may have been there since Java 5, but sometimes they would add them even, sometimes these generic functions didn't show up until later, even after Java 5. Okay, so Java has this notion of generics. It's written this way. We'll talk more about it as we go along. As we learn more ML, we'll go back and see, like, how does ML's generics, which is called polymorphism, compare to Java's generics or Java's polymorphism? Now, the reason Java didn't call this polymorphic is in the world of Java, the word polymorphism has a tendency to mean something different. Okay, so here they didn't want to call this a polymorphic list, because people in Java have been using the word polymorphism to mean something else. So they came up with the word generic list, whereas the ML people called this a polymorphic list from the start. And the ML world doesn't have the other kind of polymorphism that Java has. So this is called parametric polymorphism. So this is called parametric polymorphism. There's the parameter. Okay, so this is parametric polymorphism, parametric polymorphism. This is, okay, which Java calls generics. Okay. The other kind of polymorphism that's in Java is something called subtype polymorphism. ML doesn't need or have subtype polymorphism. But the word polymorphism in Java by itself usually it's taken to mean subtype polymorphism, not parametric polymorphism. Okay, so Java didn't want to, so ML just refers to this as polymorphic, even though it's also sometimes called parametric polymorphism. Java, well, if you ask somebody who really knows the language, they'll tell you, yes, this is parametric polymorphism, but we don't want to overload the word polymorphism anymore, so we're going to call it generics in Java. It's a generic list, which is not a bad word for it. In fact, it might even be a better word than polymorphism, because it's a polymorphism. Nobody knows what it's even supposed to mean in programming language. Generic kind of gives you a sense that it can be used in many ways. Well, actually, polymorphism, that's what it means. It means many forms. Literally what it means is morphism is the Greek word for form of something. So this is saying poly is the word for many forms. Well, this list can take on many forms: list of string, list of colors, list of objects. So it's polymorphic. Same down here. This is a list of A could be a list of strings or a list of ints. Okay? So it represents something that could take on many forms. Okay. So now back over here, when we switch from all the homework problems, all these problems were monomorphic. The list turned out to be a list of integers. And actually, in all these cases, it was a list of integers. So these functions only worked on one type, list of integer. So they're called monomorphic, one type, one form. Okay, these guys are all polymorphic. Turns out that every one of them, you actually don't even really need to know that when you write it. See, when I write it, I just all of a sudden, I look at the right-hand side and say, oh, it's going to take a list. I can tell that's a list because I take the head of it. It's going to take the head of the list. Well, head of tail of list, I know is the second item in the list. So it's making a pair of the first and second items. So here's how I write it as a pattern. I want a list broken up, deconstructed into its first, second, and the rest. I don't care about the rest. I could put y's there, but I don't need that variable. So it's better to just say, I don't need that variable. By writing the underscore, you're telling the reader, you know, it's X in front of Y in front of the rest, but I'm not going to use the rest. And then I create a pair out of them. Now this turns out to be polymorphic, but I didn't even need to know that when I wrote it. Okay. Like look at the next one. Okay. Yeah, let's do the next one. Okay. No, again, we saw here how it's polymorphic. Yeah, we saw here that we could apply the function to a list of integers, and we could apply the function to a list of strings. And I'll do one more. I could apply the function, and this is a different type, a list of doubles. Okay, there's a list of reals. Okay, see, and it gave me back real. This one gave me back string. Okay. Okay. All right. So it's polymorphic. Now this is a this is a I kind of switched gears here. These are polymorphic functions. Over here, I was really talking about polymorphic data structures. And that's one of the things that blurs this. Java has polymorphic functions, but they don't play as important a role in Java as the polymorphic data structures. And ML has both polymorphic functions, which is what we're doing here, and later we're going to do the polymorphic data structure. Well, we're using one of ML's built-in polymorphic data structures. So I'm writing a function that works on polymorphic data structures. My function takes in any G1 is a function that takes in a list of anything and gives me back a pair of those things. So I'll take a list of A and give me back a pair A. So it's a polymorphic function that makes use of a polymorphic data structure. So it's a polymorphic function making use of a polymorphic data structure. Java puts way more emphasis on the polymorphic data structures and less emphasis on the polymorphic functions. Okay, so in Java, when you talk about generics, you're much more likely to talk about the data structures than the functions. In ML, you do both. You start off with writing simple polymorphic functions, making use of the built-in list data structure that's polymorphic. Then later in the course, we'll learn how to design our own polymorphic data structures. Just like the data structures class in Java, you learn how to build your own you learn how to write your own generic lists and stacks and queues. I mean, they're already written for you in Java, but you can learn how to write them yourselves. You can write your own generic list. And most data structures books, that's what they do. They show you how to write the generic list. Okay. Okay. And we'll do the same thing. We'll see how to write this guy in ML. This guy is written in this. A generic list in ML is written in ML. It's a library feature. So just like in Java, you could a data structures textbook shows you how to write this yourself. You can use the built-in one, but you can write your own. Same thing's going to be true over here. You can use the built-in generic list, but you can also write your own. So most ML books teach you how to write your own generic list. Though there's not much use in that because it's already built into the language, but the real use is to see how it's done. See, how do you use the language to build a generic data type? Okay, so over here, every one of these, like here, fun, let's finish this one, G2. Okay, what's it do? It takes a list. We know that this is a list because you take the head of it. Okay, and then you take that item, and it's really doing the same thing this did. Notice this one put them in a pair, but this one puts the two things in a list, not in a pair. Okay, so what we'll do here is we'll just say same kind of. Actually, I can almost copy and paste this right from here to here. The only difference is I'm going to take the first item in the list and the second item in the list and put them in a list of two items. Instead of a pair of two items, put them in a list of two items. Okay, all right, and I can check over here. That's going to take in, that'll be a function. Whoops, didn't put. That's going to take in that function is generic. It's a polymorphic function that takes in a list of anything and gives me back a list of the same thing. So it's a function from list to list. Before I was going from list to pairs. I was going from a list of A's to a pair of A's. Now I'm going from a list of A's to a list of A's. But it's chopping off the list to be. Now notice it's not telling you that it's taking a list of an arbitrary number of items and giving you back a list of two items. List of two items is not a type. Okay, it's not like arrays. An array of size 2 is its own type. At least it is in some languages, like in C it is. Okay, a list of length 2 is not a type in ML. You can't say a function takes in lists of length 3 and gives you back lists of length 2. You can say it takes a tuple of size 3 and gives you back a tuple of size 2, but you can't. So tuples by definition are measured by their size. A 3 tuple is different than a 2 tuple. Lists are not measured by their size. A list of length 3 is not a type. It's not an array. An array of length 3 is a type. In Java, languages like Java and C, arrays are kind of weird. You actually can sometimes write functions that take in exactly arrays of length 3. Or you can write functions that take in arrays of any length. Sometimes you're allowed to do both. You can write a function that takes in an array of any length, or you can write a function that says, I only take arrays of length 3. Okay, so arrays can be either unmeasured or measured in their size, but not lists. Okay, so that's our introduction to polymorphism. All these turn out to be polymorphic. Okay, and you actually write that you don't even really need to know that when you solve these problems. When you just look at what this thing does and mimic it with a pattern instead of using head and tail. Just write it with a pattern instead of using head and tail, and ML will make it polymorphic for you automatically. You don't even have to say, like in Java, when you want to write things that are polymorphic, you have to write them with these. You actually have to say that it's polymorphic. One of the big differences between Java and ML is in Java, when you want to write something polymorphically, you have to declare it with all these type variables. Notice that in ML, I didn't declare it with those type variables. I just wrote it, and ML figured out what the type variables were for me. Okay, so ML figures out that it's polymorphic. In Java, you have to tell it that it's polymorphic. That's a huge difference. And that's one of the things we'll see as we compare. That's one of the things that makes ML a more sophisticated language. ML figures out the polymorphism. Java forces you to spell out the polymorphism. When you do more complicated things in Java, you have to spell out exactly how it's polymorphic. Okay. And in ML, you don't. You just write the code, and ML figures out for you where's the polymorphism. So in none of these were polymorphic. They were all monomorphic. But ML, we didn't need to know that. When we do these, if you look at the types, you see that it's always working with lists or pairs of ints. These are all polymorphic, but you actually don't even really need to worry about that because ML is going to figure that out for you. ML will, but you'll see the little type variables in all the types. You'll see the type variables start showing up. Okay. Now on the course website, I got some other problems up there for more practice with this. Okay, so these you have to write the patterns, and they're polymorphic, but you actually don't need to think about. I mean, I say that they're polymorphic types, but ML figures that out for you. So you can do the problems without even realizing that they're polymorphic. Okay. Now these problems are a little bit trickier. These problems, I give you a polymorphic type and ask you to come up with a function that has that type. Okay. Just anything. I don't care. Some function that has that type, but it has to have that type. And of course, you don't want to write 27 lines of code if you can write one line of code. So come up with the simplest function that has that type. Okay. Now, this one's an easy one because it's going to take in a pair where the first item in the pair has type A, the second item in the pair has type B. And you're going to produce a pair where this first item has type A or type B, and the second item has type A. Well, what would be the easiest way to do that? Let me download it. You can play with. Well, actually, okay, yeah, I'll download it. Now, these are a little bit harder problems than the other ones. Okay, so I want that type. Okay, well, I'm going to write my function as taking in an x and a y. Now, right now, I haven't said how to do anything with x and y. So from ML's point of view, x can have any type and y can have any type, and they don't have to be the same type. So right now, I've got that. And then, well, why not just, if x has type A and I want type A at the end, and y has type B and I want type B at the beginning, the easiest thing to do is just flip them over. Okay, that's my answer. There's my real simple function that has that type. So go down here and plug it into ML and ask ML what the type is. And you see it's a pair AB go to BA. Now notice these are not the parameters of the function. They're the types. Don't get confused. Now up here, I could write this. Most ML people won't do this. A, B goes to B, A. Okay. And then I go down here and I put that into ML. And I got to be real careful. That's why they put the little apostrophes in front of the. My control key broke on my laptop. I'm having a lot of trouble doing copying and pasting because the control key broke on the laptop. So that's why a lot of times when I do a copy and paste, it doesn't work. I have to figure out what to do with a broken control key. Okay, now see, notice that people don't use A and B as variable names in ML because that's a variable A, that's a type parameter. This is saying the function takes in a type A object and a type B object and gives me back a pair of a type B object with a type A object. Here I call the parameters A and B. That's kind of not a good idea. Yeah, because it just makes it can lead to confusion. So in ML, the type parameters are lowercase letters, and they if you need more than they always start with letter A. If you need 3 type variables, there'll be A, B, and C. If you need 4 type letters, there'll be A, B, C, D, and E. If you need 27 type letters, I don't know what they do. I don't think anyone ever has written a function that needs more than 27 type variables. That would be, you'd probably be told to go back home and rethink about what you're doing. So I don't know what they do if you actually did want more than 27 type variables. But they start with the letter A and they go up through the letters of the alphabet. So people tend to use letters from this end of the alphabet for their variables and leave the beginning of the alphabet for the type variables. But notice that type variables have a little apostrophe in front of them. So this is saying my function takes in a pair where the first item in the pair has type A, and the second item in the pair has some type B, and the output is of type B and type. Now it's not saying that this guy appears here. It doesn't have to be that. It's just saying that the type of this item is the same as the type of that item, and the type of this item is the same as the type of this item. Okay. If I thought real hard, I might be able to actually come up with a way of doing this where this one isn't exactly that one. But it's actually kind of hard to do that because generically, I don't know what A and B are, so it's hard to do anything with them. So it's hard to write. This function almost has to be that function there. This type almost has to be that, okay? Because you're saying a pair of 2 things, but you don't know anything about them. And the output pair just has to have the opposite types. So you're given, I'm going to switch, you're given an X and you're given a Y. You don't know anything about them other than that they have different types. And you have to produce something of the same type as Y. Okay. Your input's Y. And this thing has to have the same type as Y. But you don't know anything about Y. So how can you get something of the same type as Y when you don't know anything about Y? You don't have much choice but put Y there. Same here. This guy has to have the same type as X. So what goes here has to have the same type as X, but I have no idea what X is. So how can I come up with an item of the same type of X other than to put X there? The type signature almost forces me to write the function this way, okay? Now, I don't actually, this one here, I don't think there is any other way to write that type signature. I think that's the only function that can have that type signature. I might be wrong, but I think that might be the only function that can have that type signature. Some of these functions are like that. Some of these type signatures actually have this property that there's really only one thing you can write that has that type signature. And others, you have choices, but not a lot of choices. And this is one of the interesting features of ML programming. Type signatures tell you a lot. There's an old saying in ML, it's called theorems for free. And it has to do with the fact that in ML, a lot of times when you know the type, you actually know what the function is. That the language is kind of interestingly specified, that if you know enough about the type, you can almost say what the function is. In this case, I think that type may actually have only that function. And then you'll see down here later on, you'll see that like when like this is a good one. The function takes in a list of things and it's going to produce a pair. The first item in the pair has to have the same type of what's in the list. And the second item in the pair has to be a list of that type. Okay, so now I take in a list and I need the first item. I need something from the list. So X is a list. And on the output, I need something from the list and a list of that type. Well, how can I do that? Well, an easy way to do that is to break the list up into its first item and the rest of the list. Okay, break the list up into the first item and the rest of the list. Then in the output, create a pair. There's a thing of type A. I know it's a thing of type A because it's the first thing in the list. Well, how do I get a list of type A? Well, the X's. Okay. Well, that works. Yeah. Now, I'm not, notice what I did is I pulled apart the list into its first item and the rest. And I kind of just said, okay, I need an item of type A, pull it out of the list. I need a list of type A. Well, use the rest of the list. Now, can you give me another one? Like write this another way, but how much, what else could I possibly do? I'm not restricted to only this. Somebody tell me something else I could do. I need an item of type A and a list of type A. And all I know is I got my input list. Anybody has a suggestion of what I could do that's not this? What's another way to get something out of the list?
Could you use head and tail?
No, that's exactly this. This is head and this is tail. I don't want to just rewrite it. So I don't want to do this. This is just the same function. Okay, that's exactly the same function. This is written without pattern matching, and this is written with pattern matching. But notice that they both do the same thing. They take the list, break it up into the head and the tail. Take the list and break it up into the head and the tail. So that's the same thing. I want something different. I want something that actually does something different, but has this type here. Okay. What's another way to get something out of the list? What's another way to get an item from the list? What else is there besides the first item in the list? What else could I do? Yeah, you give me a list. I pulled out the first item and put it at the front of the pair, and I took the rest of the list and put it at the end of the pair. What else could I do? Besides getting the first item, what else could I do?
X, Y, and Y's?
Yeah, so break the list up into a first item, a second item, and the rest. Now, I'm going to throw away the first item in this case, and I'm going to return the second item and the rest. Okay. Can I do something else? Okay, now this F3 is not the same as this F3. Actually, maybe I'll call it F4. Okay, because that's really something different. I took the second item. So I took a list of A's and I create a pair where this guy is the second thing from this list and this is the rest. Oh, if I wanted to keep this guy here, I could do the following. I could call him Y and I could put Y in front of the rest so I could keep him. Yeah. So what I do is I'm pulling X out of the list, the second item, putting it there, and here's the rest of the list. And I could either put the first item back at the front, or I could just use the rest. What else could I do? How else can I build from this list a pair, an item of that type, and a list of that type? there's not much this function can do. Does anybody see a pattern? This F3 took the first item in the list and put it here. F4 actually took the second item of the list and put it here. What do you think this function, this type almost forces you to do what? Does anybody see there's a pattern? Any version of this function I write is going to probably have to do something that's pretty restrictive. What would be F5? What would be the next thing to do? If I don't take the first item or the second item, what else could I pick? And then I'll put the third item. And then if I want, I could either put the first item back in, and I could put the second item back in front of the, or not. I could drop them or keep them. But I'm kind of forced to make this guy one item from the list. There's really about the only way I could possibly do this is to make this one of the items from the list and this the rest of the items from the list. There's really not much else I could possibly do. So these are all kind of doing more or less the same thing, pulling something out of that list, putting it in the front of the pair, and then more or less putting what's left at the end of the pair. The type puts a real restriction on what I can do to keep it polymorphic. Notice I can't call any function on that thing. I don't know what it is. I can't call a function on it. I can't add I can't add 1 to it. If I do something like add 1 to Z, what does that do now? That's valid ML, but I kind of did something now.
Does it force C to be an integer?
And it does more than that. It forces what?
Everything to be an int?
Yeah, it forces everything because Z came out of a list, and lists have all the same type of item. So now F5 takes in a list of ints and takes the third item in the list and adds 1 to it in the front of the pair. So like let's punch this into ML. Now ML is going to say, oh, look, you did something with the Z, so that tells me what Z is. So now ML is going to say, okay, Control C. I got to fix this broken key. If anybody knows how to fix keys on a laptop keyboard, let me know. I have no clue how to go about getting a new key for my keyboard. See, I ended up with a function to take int lists now because I said add 1 to Z. So ML said that changes everything. You did something with the Z. If I get rid of that +1, it's now polymorphic. See, it's switched from monomorphic to polymorphic because I didn't do anything with the Z. So ML says, okay, it can be arbitrary type. But as soon as you do something with the Z, ML is going to say, well, only certain types. You can only add 1 to ints. And if I did this, now it's a real list because you can only add 1.0 to reals. So it becomes monomorphic. The type of Z spreads through the whole list, okay? But ML, if possible, ML tries to make them polymorphic, okay? So a function that takes a list, an arbitrary list, it gives me back a pair of one item of the same type as the list and a list of the same type of the list. There's really not much else that function can do but to pull something out of that list and put it there, okay? There's really, that function is almost not quite 100%, but very close to being specified by its type. It's basically a function that pulls something out of the list, puts it there, and then leaves the rest of the list over there. Okay. Now the rest, notice it can be kind of funny. I don't have to make it everything. I could make it everything that came after Z. I could put back the X and the Y if I want. So, I do have a lot of leeway in what I mean by the rest of the list, but this guy has to be something pulled out of the list. This one is going to have to be something pulled out of that list. And then this is the rest of the list. Okay, so some notion of the rest of the list. Okay, all right, now let's switch to, okay, now there's a lot more of these. They're kind of interesting. Part of the problem is you got to read that pattern. You got to read that type so that you know what the function takes in and what the function gives out. And then you have to think about what's the minimal thing I could do to get that type. And quite often you don't have a whole lot of choices. And there's usually some easiest thing to do. Like here, that was the easiest thing to do. Just take the first item of the list and make it the first item in the pair. Okay, and then take the tail of the list and make it the rest of the other part of the pair. So that was the easiest thing to do. And there wasn't much else leeway. And then the rest of them are kind of like that. There's usually some very simple function that has that type. And then any other function with that type is going to be some variation on that simple function. This is actually a very important aspect of ML, that when you give me the type of a function, it tells me a lot about the function. The function will quite often have that type will specify some simple function, and then any other function with that type will just be a variation on that simple function. And that's actually a powerful part of the language. One of the reasons why it's an interesting language. Java doesn't have anything like that. If you tell me the type of a function in Java, I can write almost anything. Types in Java don't quite work this way. So if you tell me a function has a certain type, I can probably do a lot of things, a lot more than I could do with ML. And you might say, well, that makes Java better. If you give me that type, I can do a lot more. And the answer is not really. The fact that this type puts a constraint on what the function can do turns out to be useful. It turns out to limit the kinds of bugs a program can have. It turns out, from a theoretical point of view, the fact that the type puts some constraint on what the function can do is actually means that the function can't be hacked, for example. It actually literally means that. It means that that function can't be taken over by some hacker and told to do something bizarre. It literally does have effects like that. It puts a lot of the people studying languages like ML right now are security people, because they're looking at these languages and how these languages actually make code more secure. Because of features like this, that there's limits to what these functions can do, determined by their type, that puts limits on what an attacker can do to the function if they try to attack it. Okay, so there's a lot of interest in the security world on these languages for their ability to specify things more rigidly, so that there's less leeway for attacking. So that's one of the reasons why these languages are becoming more and more important these days. They have security implications. They weren't invented for that reason. When they invented these languages, they were not thinking about that at all. That kind of came out years later. People started realizing that these languages actually can kind of possibly help us make code safer, more secure. But that's an active form of research right now. Okay, now let's switch gears to writing recursive functions. Okay, let's switch gears to write, because your homework assignment requires you to write some functions that are going to be generic. Okay, so let me just close those. Let's see, which one did I have? I made a change in there. Okay. Okay, so let's come up with some examples of let's do some recursion examples. Okay, here's a kind of a simple problem. Okay, I want a function that does the following. It's going to take in a a list of pairs of ints, and I want it to give me back an int list. And what I want it to do is, I have a couple versions, like version 1. I want a function fn, but I want the function to have the type take in a pair of ints, a list of pairs of ints, and give me back a list of ints. And one possibility is add the two numbers, add each pair up. So you add up each pair. So take these two numbers, add them up, and put the result in the output list. Or another possibility is find the max of each pair. Okay, or you could, that's a couple of examples. Okay, so let's try to write these. Okay, so we'll call that F1 and F2. Okay, so F1 is supposed to take in let's just think about what it's going to do. Actually, think about it from the point of view of examples. So I give it a list like 1, 2, 3, 4, 5, 5, 6, 7, 8. Okay. Now the list can be arbitrarily long. Okay. The list is a list of pairs. It's a list of pairs. And I want the output, well, for this one, I would want the output to be, well, you would take this list, you would take this pair off the front of the list and add them up and get 3. Then you take this item off the list, add them up and get 7. Okay. Now, but let's think about what we're really doing. What we're really doing is the, I'll call it F1. F1 of that list, what is it really doing? It's taking the first item in the list, which is the 1, 2 pair, adding them up and consing them onto what? The F1 of the rest of that list. Here's the recursiveness of it. Right? Because then what does that do? That gives me, well, 3. Oh, I should put I think I'll write it with a square bracket. Well, okay. Now that's going to give me 3 const on 2. Okay, what does F1 do? What does F1 do? Well, F1 takes the first item in the list, so that's 3 plus 4, and it should put it in front of F1 on what's left. Okay, well, what's that going to do? This is the recursion idea. That's going to give me 3 in front of 7 in front of, well, what does F1 do to a list? Well, it takes the first item in the list and adds those numbers up. So it'll give me 5 plus 6. And then it's going to add, it should put that in front of F1 called recursively on what's left. Okay. Okay. I'm going to keep going all the way to the end because it's important to think about what this thing does when you get to the end. What's the next step? Well, what we have so far is we got the 3 in front of the 7, in front of the 11, in front of the, okay, what does F1 do to a list? It will take the take the front of the list, which is 7 plus 8, and put it in, cons it onto F1 of what's left. Well, what's left now is the empty list. So after I pull out the 7, 8, I'm left with the empty list. Well, I should have to think now, what should that function do on an empty list? So now I've got 3 const on to 7, const on to 11, const on to 15. But what should I get? What should give me back on an empty list? What should the function do when it's given an empty list?
The result.
which should be what?
All the elements.
No,
in the
no,
list.
there's nothing. No, what does it give me? No, what does it give me here?
Oh,
What
no.
goes here? What comes after this guy? What is the result of calling this function on an empty list?
It would
The
be
list,
no list, right?
the null list. Yeah, it should give me back the null list. Now, then 3 comes down to 7, comes down to 11, comes down to 15 actually is now what I want. It's the list 3, 7, 11, 15. Okay. This is just another way of writing this. But this is how I think about it when I write my function. So my function is recursive. The function takes the first item in the list, adds those 2 numbers up, and then it applies itself to the rest of the list. It has more work to do. So the function takes what's the beginning of the list, adds them up, conses that onto the recursive work on what's left of the list. Okay, so here's what that looks like actually written out in code now. What does F1 do? Well, it asks for a X in front of the rest of the list. Okay. Oh, but what's X? X is, in this case, I know that X is a pair of numbers. So it gives me, I want an X comma Y in front of a bunch of pairs. So people would use PS for pairs. So what is this is a list of pairs. Okay. See, it's a list of pairs. So the first thing in the list is a pair. Okay. And I want that pair in front of the rest of the list. The rest of the list is pairs. Okay. Now I need to group this parentheses is grouping. Okay. This parentheses means a pair at the front of the list of pairs. And what I give you back is X plus Y cons on to F1 of the pairs. That's it. Okay. When you write recursive functions, you end up with really elegant code because you actually, it's amazing how little I mean, all this took to explain it was that little bit of code. Now let's check it. Okay. Let's start up ML. Now notice what I wrote here was exactly what I wrote in this first line. F1 on a list takes the first item in the list and adds up its coordinates, x, y, puts that in front of F1 on the rest of the list. So that's what it looks like with a pattern match. Okay. X, Y is a pair. Notice I'm using 2 patterns. This says it's a list pattern, and this says that the list is made up of pairs. This is real concise programming. ML lets you write these things in a real nice way. This is saying I have a list of pairs, and I want the first item in that list of pairs and the rest of the pairs. Okay. Okay, go over here, put that into ML. Whoops, let's see. I think I need to put parentheses around. I think I need parentheses. I need to group these 2. I think that's what's missing. I think I need to group those 2. No, wasn't that. Oh, stupid me. That what I didn't need those pairs. Does anybody see what I did wrong?
Are you using parentheses instead of square bracket?
No. Parentheses are I'm grouping. Everything is grouping. So no, this is pair. This is grouping. That's grouping. That's grouping. So over here, grouping, 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 grouping. And I don't think I need that one. Grouping. Okay. This one's pair. And I don't need square brackets. The square bracket's in here. It is a list. Does anybody see what I did wrong? What else? I made a real dumb little mistake.
Do you need fun in front?
Yeah, I forgot to declare it. I need to say it's a function F1. I forgot to put the fun in front of it to declare it. Okay, so over here, I'm pretty sure I don't need that parentheses. I don't need that one. I'm pretty sure, but I do need fun there. Okay. Right. Now, what does it do? Takes in a list of pairs and gives me back a list of ints. So it takes in a list of int pairs. It gives me back a list of ints. Okay, that's what I wanted it to be. I wanted it to be that type. Okay, now let's check that it does the right thing. Well, let's give it that list. F1 of that list. Oh, I didn't finish the definition. See, now, uncaught exception, non-exhaustive match failure. I should have paid attention. I didn't remember we had this case here. We actually had a special case here. What does the function do on the empty list? So I need to go back over here and I have to say what to do. Actually, and I have to do it in the right order. You have to specify the empty list case first. So I do the following. I'm going to say function F1 on an empty list gives me back the empty list. And then the case where it's a non-empty list looks like that. Okay. See, this is saying the list has one item in it. It's a pair. So the function on the empty list gives me back the empty list. That's the base case of the recursion. That was used over here. When we got to the end, we said, oh, the function on an empty list gives me back the empty list. So I needed to write that as a case by itself. Okay. So now okay, now I can go and do that one. Okay, see 3, 3, 7, 11, 15. Okay. Okay, so it turned out to be real simple. I mean, you always do the base case first. You know, you have to remember now the base case isn't always going to be empty list returns empty list. Here we had to think what we wanted. Since we're building up a list, we need to build it up on the empty list at the end. So we have to look at what we're doing here to see what should the function return an empty list. For example, if we were adding like if I change this function to be I'll make a small change in this function. Instead of being a list of pairs to a list of ints, I want it to just be an int at the end, and I want it to add up all the numbers. So I want it to just add up all the numbers. Okay. Now here's how that would change the definition. I'll call this F2. When you get to the end, when you get here to the end, well, first of all, you change these to being additions, change these guys to being additions. So I take each pair, add them together, and add them up to the result of the function on the rest of the list. But now the result on an empty list should be 0. Now I'm adding up all the numbers. I'm taking all the pairs and adding them up. I'll call this F2. So notice that the base case changed. If I want to add them all up, then when I get to this guy, I should be adding up and put a 0 here, not an empty list here. Okay. So the base case, sometimes the base case would be return 0. Sometimes the base case could be return an empty list. It kind of depends on what you're doing. But you have to think, what do I do on an empty list? Okay. In this case, okay. Let's see. Oh, Now I need grouping. I think now I need the grouping here. I think. No. Oh, well, notice that the back up arrow didn't work right. Up arrow only gave me back one line of up arrow. So I think I can go up here. I think I need grouping here. The grouping in ML is kind of quirky. You're probably better off putting parentheses around everything. There, okay? No, I still have the same problem.
Is it because of the zero? Like it says a pair of ints, but then operator domain, pair of ints, and then operand and
Is
int and list.
a pair, an int, and an int list.
So maybe having that zero there is throwing it off.
Yeah, I think it is. See, I'm trying to remember how I would rewrite that now. I wanted to add up all the numbers. So I'm thinking, real quick, but add up those two, then add them up to what comes next. So this would be up, you would change this to an add, and then this should be the sum of the rest of the items. Okay. So all the conses should change to pluses. And at the end, this guy should return a 0 instead of an empty list. Okay. So the right idea, but I'm probably just not saying it right here. Okay. No, I'm drawing a blank. I'm not, we run out of time. Yeah, I'm drawing a blank on what I did wrong to add up, which is, perfectly reasonable. Instead of giving me back a list where I add up this one and then add up this one, why not just add them all up? So I would return just a single number that's the sum of all of them. Okay, so that's a perfectly well-defined idea. Take in a list of pairs and just add up everything in the list of pairs into one number. And I would take the first item in the pair, the first item in the list, which is a pair, add up the two numbers in the pair, and add them to the result of the rest of the list. So I'm not sure what, and I think it's got something to do with the 0. It's not liking that, but I'm not sure how else to write that. When it gets to the empty list, it should just give back 0. Because at the end here, when we call this F2 on the empty list, we want to be adding up and have a 0 here at the end. So I have to think about that. I'm not sure if it's just a matter of I got parentheses mixed up somewhere or what I'm thinking wrong, but we've run out of time. So on next week, we'll do more examples of recursion. We'll do more examples of thinking this way. Notice that, this is the key idea here. You think of what the function's doing. You think, oh, it's taking the first item, doing something with it, okay? And then it takes that item, and then there's the recursion. Just add up what's the rest, do something to the rest of the list.
If you put the 0 in brackets.
Your F2 is calling F1.
Oh, is it that stupid? Yes, that's stupid. Yeah, thanks. That was the stupid mistake. Yeah. Boy, it can be hard to find these little bugs. See? Yeah, that was the stupid mistake. It was the right idea. It was just a real dumb copy and paste. Copy and paste is your friend, and copy and paste is your worst enemy. It's so dangerous to use copy and paste. Okay, so I just copied and pasted that, and I forgot to change one of the functions. Okay, so now again, check that it'll give me the right answer. Now call F2 on this list, and it'll add up the list. Okay, so it's easy to change it. So it was easy to change it from adding up the pairs to adding up the whole list. But yeah, I did a bad copy and paste. I forgot to change that one there. Okay, thanks. That could have taken an hour to find that mistake. Okay, that's why copy and paste is good and bad both. Okay, all right. So we'll do more examples. I'll put some problems. I'll put some descriptions of problems up on the course website, and then we'll solve. And if you want, you can look at them over the weekend, and then we'll solve them. Do more examples like this. Once you've done 4 or 5 of these, they start becoming pretty easy. I think we're specifically doing one kind of recursion on lists. And recursions on lists is the easiest kind of recursion there is. And it's a good way to learn the idea of recursion, because recursion on lists is the simplest form of recursion. So that's what we're going to emphasize, recursion on lists. Later on in the semester, we'll do more fancy kinds of recursion, but recursion on lists is actually pretty straightforward. Once you've done a few, I think you'll get the hang of it and you can do a lot of them, okay? And the book does some examples. There's some examples in the book. And like I say, the homework problems, a couple of them are recursion on list problems, okay? All right, so I'll quit there. If you have questions about the homework assignment, come to office hours or send me an email. And look at these problems that are up on the website, because ML, it helps when you're learning ML to have something to think about. So that's why I put these little lists of problems up there. They give you something to think about. They're not, everyone's a little one-line problem. The key is thinking about them. I think they are a good way to think about ML. And the way you think about these, we're going to need. We're going to keep doing more sophisticated things with ML. So we're eventually going to be writing code that traverses trees in ML. So we're going to do data structures and algorithms in ML. We'll get to data structures and algorithms in ML, and it's pretty interesting. And this, you need to do these little things before you can do the big things. So these little things need to think this way, need to be able to think this way before you can do the more complicated things we'll be doing later on. Okay, so I'm going to quit sharing there. Anybody have any last second question? If you have a question about the homework, send me an email or come to office hours. Okay, so have a nice weekend. Bye.